Hello. Today we will see the small signal analysis of 5 transistor operational transconductance amplifier. So this video is going to be very important to understand the small signal analysis and how we can analyze the 5 transistor OTA in a quick way just to design the circuit. Okay. So in a designing perspective, I'll explain you how we can see the circuit. So what you can see here is this is common mode input voltage and this is the difference in the 1 and 2. So V1 minus V2 is delta V in. Point number 1. Point number 2 is V out is calculated with respect to ground. Okay. So let's see and analyze the small signal analysis. So before going to that, I'll explain you. I wanted to share one thing that can we apply, I want you to see the circuit and just see and look, can we say that is virtual ground applicable here? Can we use the concept of virtual ground here? When, note that, most important thing, when this potential is not 0. Okay, this potential is not grounded or 0. It's just a voltage with respect to this voltage with respect to ground. Okay, so in that case, let's see if we can say that, how we can see that, and we want to know is can we apply the virtual ground concept here or not. By assuming we are not, if we are not assuming the virtual ground concept, okay, let's see how to see the circuit. So from left side, let's say it is increased by some amount. We know that here the inversion will happen and the amount of inversion will be dependent upon the what? The current through this M1, the current through this M1 and the equivalent resistance calculated here. And the equivalent resistance calculated here is 1 by GM3, okay, and the resistance C from here to down. So if we don't assume the virtual ground here, then this will be R01 1 plus GM1 multiplied by 1 by GM2. So if you see, it is approximately 2 delta 1 and the equivalent resistance is 1 by GM3 parallel 2 times of R01, and we can say that equivalent resistance is 1 by GM, let's say, okay, because 2 R0 is very high. So point number 1 is the amount of change is delta I times the R equivalent seen at this node, and that is 1 by GM3. So delta I 1 by GM3, point number 1. Second thing is, here you have opposite decreased. Since you are increasing here, you will decrease here, basic concept. Now at this potential VB, the inversion will happen and the amount will be decided by the current through this I2 and the equivalent resistance seen here. And what is the equivalent resistance? It is R04 and the resistance seen downward from this B point, and that is R02 1 plus GM2 multiplied by resistance seen from here 1 by GM1, and that is also equal to approximately 2 times of R02. Now the equivalent resistance is R04 parallel 2 times of R02. Now the voltage amplitude difference in the change because of this here is delta I2 divided by delta I2 multiplied by R04 parallel 2 times of r02. So you can see from here, you can see that this and this are not same. Okay, so if this is this much amount, then this change is very high. Okay, so we know for the virtual ground concept, this two potential has to be equal and opposite, then only this potential can be said to be virtually ground, VP. So if you want to know the concept of virtual ground, you can visit this part 2 where I have explained everything about the virtual ground. And in that, what is the important thing, that this potential A and B should be equal and opposite, then only we can say that VP will be 0. Okay, but here magnitudes are different, then because of that we cannot apply the virtual ground concept here. Only thing you have to notice here is that this point VB is open circuited. Open circuited means the voltage is calculated between this point and ground. Okay, so this is the voltage V out. Okay, so we cannot use the virtual ground concept here, point number 1. Now let's go in the approximation. We know that we cannot use this virtual ground concept, but let's see and analyze in terms of how we can analyze the circuit. So if you know that the voltage gain is equal to short circuit transconductance multiplied by R equivalent, R out from that point. And here if you see in this circuit, what will be the V out comes out. Finally, if you see, the V out will be minus, the voltage gain will be negative of the GM of 2 multiplied by R0, R equivalent from this point will be R04 parallel R02. So this will be the value. Let's see how we can calculate this. So first we will calculate the short circuit transconductance. So this will be the diagram, that this will be the grounded, this will be grounded, and short circuit means we will short this and calculate the current from here, and this is open circuit, this is plus V in by 2 minus V in by 2. Okay, so before that also, before this, if you see the circuit closely, is this potential 0? Is VP is 0 or not? Okay, so I have made a video, separate video for that. If you want, you can visit that, and there I have explained you that in approximation we can say that this potential will be 0. Still here I'll explain you in a brief way that how VP is 0. Okay, so if you see clearly, this is ground. Okay, so this potential is 0. Now we know that if one potential is 0, for virtual ground other potential has to be 0 also, then only it will be virtual ground. Now let's see what is the concept here. So if you visit that video, in part 1 I explained, in part 1 of virtual ground I have explained that if this potential is 0, both potential, then this will be 0. And in second part I have explained that what the delta change plus 2 minus 2 equal and opposite, then also this will be 0. Okay, so here one node is ground 0, and potential here at point this is defined by the how it will be defined. If you see here, it will be defined by the current through this and R equivalent at this, and we know that that is delta I1 by GM4, and that is GM4 or GM3, both are same, 3 and 4 sizes are same. Okay, so this will be approximately equal to 0 volt. This is the approximation we have taken, not exactly 0 volt, not exactly, but approximated, because the swing is very small. In that case, if you see, the circuit will become like this. This is ground, this is ground, this is approximated to ground, this is plus V and this is this, and this circuit will be is for short circuit transconductance calculation. Okay, short circuit transconductance calculation. If you ground this, then only we are checking if we can use the virtual ground concept or not. So this is the circuit. Now split this circuit and see what will happen. So whatever the change in this current, will be same in this branch. So there is no change in this R0, and this potential is defined by the change in current in R0. These two R0, whatever current changes here will define the potential change here. And if these two currents are same, then there is no current in this R0. That is what I have explained here, that whatever change here will be taken by here, and since it is 0 volt and 0 volt and no current here, this potential will remain same because current is 0. So if R is current from delta I, basically change in current is 0, then and this is 0, then this potential change will be 0. Delta V is 0 volt. Okay, let's see example. Just I want to explain you the virtual ground concept simply. Let's say it is 1 volt initially, and you have increased the current by 1 ampere, just for the example, and that current increase is taken by here. Okay, is taken by this branch. So, and this is 0 volt. So there is no change in the current in this IR in both resistance. Hence, the voltage defined here will be no change. There will be no change. So that is why VP, just go and see and analyze this, that why this VP is 0 here in approximation. Okay. Now coming to the calculation of the short circuit transconductance, simply what we will do, if this is ground, okay, if this is ground, the current through this is GM times of whatever VGS, and VGS source is now 0, and this is V in by 2, and this current will be same as this current, so M3 M4 same, and current here will be defined by the GM times of input, and input is VGS, that is minus V in by 2, and so total current, if we apply the short circuit KCL, the total current will be what? Let's see here. This is GM V in by 2, and in this direction it is minus GM V in by 2. But so what will happen? In opposite direction it is GM V in by 2. So total current from here and here, it will be GM V in, but short circuit transconductance is direction, current is this, so it will be minus GM V in. So this is the short circuit current, and the transconductance will be minus GM of 1 and 2. Okay, so only thing is that you have to see the virtual ground concept here in approximation. Now we got that the GM short circuit is GM2 minus GM2 or GM1. Now let's see the R out. So how we will see the R out? Okay, for R out, open circuit, this will be ground, this will be ground, this will be ground, this will be ground, some voltage source and current from that voltage source is will be used for defining the R out. So if you see here, important point before going to here further, this total current will be current through this branch and current through this branch. That's it. Okay, and here VGS is somewhat looking 0 or what. So whatever the current, let's say this, whatever the current through this, will it go from the GMVGS or not? This current IM2, will it go from this or this only? This. So to simplify this, I have made one video where the Thevenin equivalent across this point has been calculated, and from there if you see the Thevenin equivalent circuit, not R equivalent but the Thevenin equivalent circuit, we have R equivalent is 2 times of R0 1 or 2 and VTH is 0. So we can replace that here and we have 2 times of R0 2. So it will help us to understand, to analyze to calculate the current. Okay, now let's see. So if we make the small signal model, 1 by GM3, 2 times of this, and there is one dependent current source GM4. Since it is a PMOS, so current direction will be from source to drain and the magnitude is defined by the VSG. Okay, current is from source to drain and voltage magnitude is defined by the GM-VSG. If we calculate this, it will come like this, minus GM4 VA. VA is this because G gate is connected. So by this, if you calculate, VA is whatever current going through this and GM3. So this, and it will be equivalent to minus IM2, and it is obvious that from this whatever the current will be going through the dependent current source, because the voltage from this voltage is generated through the current of this branch. So that voltage will all again convert that into current. Basically what I mean to say, whatever current here IM4 will make the voltage, and this voltage will again make the current, will make again one current which value is defined by the same GM. Because of the same GM and because of the same GM, this current will be same, that IM4 and IM2 and IM4. Okay, so this is this, and now we have R04. So from just see how I have calculated the value of current GM VSG, source to ground, source to drain, the current direction, and the voltage is from source to gate. Okay, because source potential is higher than the gate potential. So this is way of writing the current, and in this way you will calculate, it will be minus IM2, and IM2 is nothing but voltage at this potential divided by total resistance, and total resistance is 2 times of R02 1 by GM3, and here you can see it is Vx upon 2 R02. So what is the KCL? KCL is nothing but here IM4, it is IM2 equal to here also IM2, and there is one resistance, across this the current is Vx upon R0. Simple. This potential is Vx and this is Im2. Just visit this circuit again and see that how this is Im2, because simple, the current will converted to some voltage, and same voltage is converted to current through same GM. So that is why Im4 is Im basically the dependent current source is equal to Im2. Okay, now if you apply the KCL and solve it, then you will simply get that R equivalent is R02 parallel R04. So what is that? This is V out, so this will be R04, this will be R02, so both are in parallel. So by this way we have calculated the value of R equivalent, this one, that comes out to be R02 parallel R04. So only thing that you have to take out from this complete video is that for this complete circuit the gain is defined by the GM of these two, either GM of these two, and multiplied by the resistance seen from this R04 parallel only the resistance of R02, not equivalent, just R02. So R04 parallel R02 is the resistance and GM1 is the equivalent GM of this circuit, and negative direction because it will be what? The phase change. Okay. So this is the complete value, a complete small signal analysis of the 5 transistor OTA.